everyone, I am Dr. Mohammad Ghulam Murtuja, currently working as an assistant professor in the Department of Mathematics at SR University Warangal. So I am pleased to share that I have started a lecture video series on few important topics in linear algebra, which is specially designed for engineering students. So in the first lecture, I will be discussing the concepts of column space and null space with a clear explanation and some examples. So stay tuned and keep watching me. Thank you. So coming to the definition of column space. So column space is a column space of a matrix is a vector space that contains all linear combinations of the columns of A. So what is vector space? You know that vector space is a set of all vectors over a field which can be real number and complex number, and if it is satisfying 10 properties including closure and associative, distributive, identity, zero vector, all these things, along with two operations, one is plus addition, one is multiplication. So along with these two operations, if a set of vectors, suppose V, is satisfying 10 properties including I already discussed closed property, distributive property, commutative property, then zero vector is there or not, identity, inverse vector, all these things. So I'm not going to discuss the vector space details here. So column space of a matrix A is also one kind of vector space which will contain the linear combination of the columns of A. So suppose A is a matrix like 1, 2, 3, 4. I am taking an example of 2 by 2 matrix. So if you see the columns, it has two columns. So the linear combination meaning is that if we take two constants, arbitrary constants C1 into the vector column vector first 1 3 plus C2 into the second column vector 2 4. So this is called linear combination of the column vectors. Now if we give the set form, so this total set is called a linear combinations of columns of the matrix A. Now this is another name of this is called span. So column space is nothing but the span of column vectors. That means how many columns you have, take that many of constants and multiply the first constant with the first column vector plus second constant the second column vector, and if you find that different kind of combinations by choosing the C1 C2 constant values, so all vectors will be the part of the column space, rather you can say span of the column vectors. So this is the definition of column space of a matrix. So you know that if a matrix order is m cross n, so the first m is denoting the number of columns, number of rows, and the n is denoting number of columns. So definitely when we are taking columns, so definitely it will be a subspace of r to the power m, right, not r to the power n, because like suppose if you write a matrix 1 2 3 4 5 6, so the order of this 2 3, so first is denoting the number of row and second is denoting the number of columns, right? So these columns we have to take, so C1 into this, C2 into this, C3 into this, so this will be the column space of the matrix. One kind of application of column space is that in system of equations, which will be our next topic to be discussed, so we'll discuss that concept later. So if you see the system of linear equations, if you get, and if you see the matrix from Ax equal to B, so this system of equation will be solvable if and only if, that means it is necessary and sufficient condition that the right hand side vector B must be in the column space of the coefficient matrix A. So we'll discuss this later. So this is one special important application of column space, right? So if you see a few more examples, like this is identity matrix, 2 by 2 identity matrix, you know. So if we find the column space of this matrix I, so you can easily see that the C1 into the first, C1 into the first plus C2 into the second column. So ultimately if we calculate it, you will get C1 into 1, so C1 plus C2 into 0, so 0, so only C1, and second term only C2. So this is nothing but the set R2. What is R2? Ordered pair elements. So you can see you are getting ordered pair elements. So you can choose any C1, C2, you will get the R2 elements. So the R2 can be represented by C1, C2. So this span, as I already discussed, span is the linear combination of these two vectors. So that means the column space of I is nothing but the R2, because you are getting the elements C1, C2, which will be represented the R2 order pair elements of. So another example is this one. If you take this, so C1 into 1 by 2, so if we solve this, you will get the first one, second one is nothing but the multiple of first one. The first column is 1 2, second column is 2 4. If we take 2 multiple of the first column, you will getting the second. So directly you can say this is the y equal to 2x type form, right? So if x equal to 1, y is 2, if x equal to 2, so y is 4. So you are getting this. So the column space of the second problem is nothing but the y equal to 2x type. That means the line through the origin. So these are the few examples of column space. Now coming to the definition of null space. So definition of null space is that null space of a matrix A is also a vector space, and in that vector space what kind of elements will be there? The elements of this vector space will be vectors which will satisfy this homogeneous equation. This is called homogeneous equation, that also we will discuss later. So that means a matrix is given A. If we multiply with this A column vector, suppose x1, x2, x3 like that, it will be depend on the A. If A is having 2 rows, then it will be only 2 element vector. If A is having 3 rows, it will be x1, x2, x3, that means 3 element vectors like that. So if we multiply A with this one vector, non-zero vector, and after multiplying, if you are getting the 0 vector, then this all collection of the solutions of these equations will be called the null space of the matrix A, right? And as I discussed already, that if it is m by n matrix, the order is m and m by n, then the column space will be the subspace of R to the power m. This will be the column space of A, and null space of A will be the subspace of R to the power n. You have to remember this. Okay, so this is the definition of null space. So that means a matrix will be given to you. So to find the null space of the matrix, you should multiply a non-zero vector in the A, and it should be equal to the 0 vector. Then if you solve it, then you will get the vectors x1, x2, x3. So that much of what kind of solutions you are getting from here, this set of all the solutions, like if I write this, suppose it is 3 by 3 I am taking. So this all the solutions of x1, x2, x3, this will be the null space of the matrix A. So if you see this example, so again, as I discussed, this is 2 by 2 matrix. So definitely we will take 2 element vector x1, x2, and must be equal to 0 0. So the solution of this will be called the null space. So if we write the equation form here, so you will get x1 plus 2x2, this row and column multiplication, equal to the 0 vector. Similar ways for the second row, 3 into x1, 6 into x2, row into column is equal to 0. If you see the second equation, if you take common 3, you are getting same as the first equation. So x1 plus 2x2 equal to 0. Here also you are getting, here also you are getting. That means x1 is nothing but minus 2x2. So that means the solutions types are all, if you take x2 equal to k, so x1 is nothing but minus 2k. So the all solutions are getting, you are getting minus 2k and k. K is any constant non-zero. It can be 0 also. Right? So this kind of form of the solution. So if we write in the bracket, if you write in the bracket, So this will be called the null space of this matrix A, right? So the solution of this kind of equations, Ax equal to 0, that means this is called homogeneous. We'll be discussing later what is homogeneous, what is non-homogeneous. So you can remember like that, that this is the solution of homogeneous system of the matrix A. So this is the solution form. So this will be the null space of the matrix A, right? Now coming to one important concept, which is called basis of column space and basis of null space. So as I already discussed, that column space is the combination of the column vectors, right? And null space is the solution of the homogeneous system. Now basis definition is that, what is basis? Basis is, it will be span of the set and all the vectors in that set will be linearly independent, right? This is the definition of the basis. It will span the set. Suppose the set is V, so it will span the set V. Suppose B is the basis, so B is the basis, so it will span the V, and all the elements of the B must be linearly independent. Now in the previous examples we said that the combination of the column space are called the combination of column vectors are called column space. Now to find the basis of the column space, we have to choose which columns are linearly independent. What is meant by linearly independent? So suppose you have u1, u2 and u3 vectors. Now linearly independent means if these three vectors will be called linearly independent if you take c1 u1 plus c2 u2 plus c3 u3 equal to 0. 0 means 0 vector, not the 0. This 0 is 0 vector. Now after solving this, if you are getting all c1, c2, c3 as 0, that means it is called linearly independent, Li. So this is the process to check that these vectors are linearly independent or not. If you are getting any of this c1, c2, c3 is non-zero, any of this c1, c2, c3 is non-zero, then that means these vectors are not linearly independent. This is linearly dependent. So this is the concept of basis. So in the column space also, which columns are linearly independent, we have to find it, and we keep in the set. This will be called the basis. Similar way, what are the solutions you are getting for the null space, then check that what are the set of the solutions are linearly independent. Not all the solutions, we will check only the linearly independent vectors. This is called the basis of null space. Clear? This is the concept of basis of column space and null space. So we will solve problems. So we have taken this real life situation problem. Suppose a factory is studying 4 products, that how it affect the load of 3 machines, right? So they have observed some product effects and repetition of others and do not introduce any new load. So the relationship they have measured using this matrix, right? So this is the matrix is given by so the relation, this is representing the relationship of this product and the machines, right? Now we have to find the basis of column space, which will be representing the minimum set of independent machine load patterns, and basis of null space, which will be the independent combination of products which overall machine load will be 0. As I discussed, it will be Ax equal to 0, and this will be the minimum, that means minimum independence machine load patterns. That will be the basis of column space. So now we will do some mathematics to find the basis of column space and to basis the null space. Okay, so for this concept, to solve this kind of problem or to find this kind of basis of column space and null space, we should note 2 important concepts. One is called row econol form, and row reduced econol form. Okay, so row econol form means a different kind of form of a matrix, where we'll get a matrix like that. So let me discuss this. So I'll discuss here. So REF, row econol form, means a special type of matrix where the pivots means the first non-zero pivot, means first non-zero element in a row. So this will be the pivots of the row. So a row econol form means if we see the first non-zero element here, suppose this is 2, 3, 4. So row econal form means the below element of the pivot must be 0. So if this is the first non-zero element in the first row, so below elements must be 0. Now I am taking the second pivot in the second row. So suppose this is the second pivot. So again the below element of this pivot must be 0. And if you take 5 here, so suppose here I am taking the third pivot. So this third pivot is this one. So the row econal form means the pivots would be the right side of the previous pivot. You see the second pivot is the right side of the 2, third pivot is the right side of the 3, and the below elements must be 0. This is row econal form. Now if you see the row reduced econal form, so row reduced econal form means the pivots must be 1. First of all, there will be 2, 3, 6, this will be not considered. So the pivots must be 1. If the same example if I take, so the pivots must be 1. And second condition is that the below and above of the pivots, if this is the first pivot, second pivot, third pivot, below elements are already 0, the above must be also 0. So that means if 1 there is no above element, but the second pivot there is a above element 3, so it should be 0. You have to make it 0 by using row operations. Similar way, this is the third pivot, the above 2 must be 0. So now this is called RREF form. This is called row econal form. So RREF form we are going to use in this problem to find the basis of column space and basis of null space, right? So RREF form means the pivot must be 1 and the below elements and the above elements of the pivot must be 0, right? And what are the pivots called? Pivots means the first non-zero element in a row. So if you see the first column, first row, so this is the non-zero element, first one. If you the second row, this is the first non-zero element in the second row. In the third row, this is the first non-zero element in the third row. So these are called pivots. So if check the below elements of the pivots must be 0. So first element is 1, 2, 0. In the third pivot there is no below element, so no need to check. And the above also must be 0. So in the first pivot there is no above element. For the second pivot there is above element, it must be 0. Third pivot also there are 2 above elements, it should be must be 0. So this is the concept called REF and RREF. We are going to use this concept to find the basis of column space and null space. So what is the first step to find the basis of column space is that if a matrix is given, so you just convert this matrix to the row econal form using, row reduced econal form using the row operations. You know you have 3 row operations. One is you can interchange rows, any row to any row. Second is that you can add or subtract any row to any row. And you can multiply a constant, or you can say scalar, multiply a scalar to any row. So these 3 are allowed in the row operations. So using these 3 operations, we are going to convert the given matrix to row reduced econal form, right? So the first step is just write the matrix, what are the given. So if you see, this is the matrix is given to you. Now you are using the operations to reduce this matrix to row reduced econal form. So you are going to first, as I discussed, this is the first pivot you are getting. So these 2 elements must be equal to 0. So to make this and this to 0, you are using row 2 is row 2 minus 2 row 1. So 2 minus 2 will be 0. Again same thing, row 3 is row 3 minus 2 are 1. So this 2 minus 2 will be 0. So you are using these 2 operations simultaneously, you are getting the below elements as 0. So 2 minus 2 0, 4 minus 2 is 2, 14 minus 10 is 4, 4 minus 2 is 2, then 2 minus 2 is 0, then 3 minus 2 is 1, 12 minus 10 is 2, this. So you are getting this is now first pivot, this is second pivot. So as I discussed, the below elements of the second pivot also must be 0. And we have to remember that these pivots must be 1, because as I discussed, we have to reduce to row reduced econal form. You see RREF, right? So we are making these pivots at 1. So you are dividing 2 in the second row. So R2 is R2 by 2. So you are getting, now you are getting the first pivot is 1, second pivot is 1. Now you have to make the below elements is 0. So to make the below elements 0, you are using R3 minus R2, right? So R3 minus R2 if you are using, so this 0, 0, 0, all the below, what is called, the bottom row you are getting 0. Okay, one more thing I forgot to add, in the row econal form or row reduced econal form, in the both cases, if you have 0 row, any 0 row, then it should be placed in the bottom. This is also one condition. If you have any 0 row in these two forms, 0 row means all elements in a row are 0. So you have to make it in the bottom, because you can interchange the row as I discussed. So you can just interchange the row and you make it in the bottom. You just bring it to the bottom of the matrix. Okay. So here we have already used some operations and we made it to row reduced econal form. And also I discussed that this is the second pivot, so the above element also must be 0. So this above element must be also 0. So I have used this R1 minus R2 to make this 0. So now this is in the row reduced econal form, because all pivots are 1 and above and below elements are 0. But you can see this is a 3 rows and 4 columns. It is a 3 by 4 matrix, but we got only 2 pivots, because in the third row you don't have any non-zero element, right? So there is no pivot. So only the first row you have one pivot, in the second row you have one pivot. So 2 pivots you are getting. Now you check these pivots exist in which column. So if you see, the first pivot exists in the first column and the second pivot is exists in the second column, right? Then the third column there is no pivot. If you see the circles, in the fourth column you don't have any pivot. So only you have the first column and second column. So you take the corresponding columns from the main matrix. Please remember this thing. So you check the pivots exist in the first column and second column in the RREF form, but you take the same positions from the corresponding matrix, original matrix. So this is the first column 1 2 2, this is the second column 1 4 3. So this, if you put in the bracket in the set form, this is the basis of column space. Although it has 4 columns, but these two are not independent, so only these two are independent. That's why you have given here, right? So this is the basis of column space. So how to find the basis of column space? Please remember, write the matrix, given matrix, and convert to row reduced econal form. Row reduced econal form means the pivots must be 1 and the below and above must be 0. Okay, so now count the pivots, where you are getting the pivots. If it is exists in the first column and second column, so take the first and second column. If it exists in the first column and third column, you take first and third from the matrix. So here you are checking that pivots are exist in first and second column. So the corresponding column from the main matrix, given matrix, we are taking, and this is called the basis of column space, right? Now finding the basis of null space, it is follows the same process as I discussed. It is the solution of Ax equal to b. So we are taking the previous, we have done now this RREF form. As I already discussed, this RREF form we are going to use. So this is the RREF form of the matrix. Now we will solve this RREF form. That means suppose we are giving a name in B, so we have to solve Bx equal to 0, and the solution of Bx equal to 0 will be the basis of null space. That means the given matrix was A and we have converted to row reduced econal form to find the independent solution of the homogeneous system. That's why you are not using Ax equal to 0. Now you are using Bx equal to 0. B means the RREF form of the A, not the A itself. Okay, so you are going to use the RREF form which you have already calculated in the previous slide. So this is RREF form. So we are going to discuss 1 0 3 0 0 1 2 1, all are 0, and we'll going to multiply. So is at it has 1 2 3 1 2 3 4. So we have to use 4 vectors, sorry 4 component vectors, as it has 1 2 3. So you have to multiply this row into this column. So how many columns you have? 4. So you have to use 4. Okay, using 0 vector, right? So if we calculate this, so 1 into x1 plus 0 into x2 is 0 only, 3 into x3, 0 into x4 is 0 only, equal to 0, first equation. From the second equation, 0 into x1, so 0, 1 into x2 plus 2 into x3 plus 1 into x4 equal to 0. In the third equation, all are 0, so nothing to write here, 0 equal to 0. So you are getting only two equations, right? Now you have to solve it. So you remember one thing is that if you have four variables like x1, x2, x3, x4, four variables, so you have to find the four solutions, four variables, that means the value of x1, x2, x3 and x4, but you have only two equations, one equation, two equations. So that means four variables minus equations, you have two less equations, so these two will be the free variables, right? Okay, so if number of variables is 4, number of equation is 2, just make a minus, so that much of variables you have to take free. So suppose I am taking x3 as k1 and x4 is k2. So if you substitute here in the first equation, so you will get x1 equal to minus 3k1, right? From here you will get x2 equal to minus 2k1 minus k2, because x3 is k1, x4 is k2, you have taken this side. So the final solutions you are getting here, if you write here, final solution you are getting x1 is minus 3k1, x2 is minus 2k1 minus k2, x3 is k1, x4 is k2, right? So this will be the final solution. So the finding the basis of column space, sorry, basis of null space, what to do? So you just write the solutions here. So what is the solution we are getting? x1 is minus 3k1, x2 is minus 2k2 minus, sorry, 2k1 minus k2, x3 is k1 and x4 is k2. Now just separate this k1 and k2. So k1 you are getting minus 3, minus 2, 1, 0. k2 you are getting, there is no k2 in the first term, so 0. Second term is minus 1. Third term is no k2, 0. Fourth term is 1. So this one and this one, these two are called the basis of column null space. So if you see, as I discussed, so these are going to, these two are the basis of null space. So if you write in the form, it will be the basis of null space, right? So what is the process to find the basis of null space? Just take the RREF form from the column space itself, then RREF form into the vector x1, x2, x3 is depends on the number of columns, equal to 0 vector. Then solve it. If you see the number of equation is less, take that much of variables as a free variables. Free variable means you have to take some parameter values, k1, k2 like that. Then solve it, find the value of x1, x2, x3, then put in the bracket, just separate the k1, k2, separate the k1, k2 and take the vectors. These two vectors, these are the basis of null space. So basis of null space of A is nothing but, in the bracket we can write minus 3 minus 2 1 0 0 minus 1 0 1. So this is the basis of null space. So in the similar process we can solve this problem also. So if we take this problem, so you can try it. So I am taking any other example, suppose 2 3 4 2 4 8 and 9, then 3 6 9 12. Suppose this is the matrix I am taking. So similar way to make this RREF form, we are going to use row 2 is row 2 minus 2 row 1 and row 3 is row 3 minus 3 row 1, because 2 minus 2 will be 0, 3 minus 3 will be 0. So using these two we are going to solve it. So first row will be as it is, So 2 minus 2 is 0, 4 minus again 4 is 0, 8 minus 6 is 2, 9 minus 8 is 1, 3 minus 3 is 0, 6 minus 6 0, 9 minus 9 0, 12 minus 12 0. So you are getting this is first pivot, this is second pivot. So below elements are already 0. So you have to make this pivot is 1. So I am going to use R2 is dividing by R2 by 2. So you are going to solve it. So 0 0. So this is 2 by 2 1. This is 1 by 2. 0 0 0 0. Now this is the first pivot. This is second pivot. So above element also must be 0. So I am going to take this one. Row 1 is row 1 minus 3 row 2. So 1 minus 0 1 2. This is 3. So 4 minus 3 by 2. 4 minus 3 by 2. So you are getting 8 5 by 2. 5 by 2 0 0 1 1 by 2 0 0 0 0. So this is the RREF form because this is the first pivot, this is the second pivot, and the below elements are 0. Sorry, this is 0, and third above element also 0, right? So this is RREF form of the matrix A. Now you can see that you are getting two pivots in the, this is first pivot, this is second pivot. But if you check the columns where you are getting the pivots, it is the first column and the third column. In the second column there is no pivot, in the fourth column there is no pivot. So first and third. So from the main matrix we will take the first and third. So the basis of column of A, column space of A is nothing but the first 1 2 3 and the third 3 8 9. So this is the basis of column space, right? Now you are going to use this RREF form again for null space. So for null space we are going to use the same RREF form of the matrix. Okay, so if you take the same matrix you will get 1 2 0 5 by 2 0 0 1 1 by 2 then 0 0 0 0 into x1 x2 x3 x4 equal to the 0 vector, right? Now you are going to solve this to find the basis of null space, right? So if you write the equation form, so x into 1 x1 plus 2 into x2, 0 into x3 will be 0 only, 5 by 2 into x4 equal to 0. From the second equation you are going to take x3 plus half x4 equal to 0. Because first is 0, second is 0, so there is no x1 x2, and last row is the 0 equal to 0, so no need to write. Now again it has two equations and four variables x1 x2 x3 x4, so 2 will be the free variables. Two variables will be free. So that means if you take x3 is x4 is k1 or x3 anything, so I have to take x3 is k1 and x4 is x2 is, so okay, so take x4, it will be easy to for you. So I am taking x4 is k1 and x2 is k2. So from the last equations you are getting x3 is minus 1 by 2 k1. Now substitute x4 and x2 in the first equation, so you are getting x1 equal to this side, so minus 2 k2 minus 5 by 2 k1. So if you write the solutions you will get minus 5 by 2 k1 minus 2 k2, this is x1 value, x2 value is k2 only, x3 is minus 1 by 2 k1 and x4 is k1. Now you just divide k1 k2, so if you divide k1 you will get minus 5 by 2, this first term, second term there is no k1, so 0, the third one is minus 1 by 2 and it is 1. This is k1 plus k2 into, there is minus 2 in the second, there is 1 in last and second last, there is no k2. So this is this comma this is the basis of null space. So this was the concept today. We have discussed about column space, null space, their definitions, then the most important topic, basis of column space or null space, and how to find them with some example. So in the next class we are going to discuss, next lecture we are going to discuss rank of a matrix. Then we will go to the topic system of linear equations. Okay, thank you, keep watching.